So today we are going over everything exponential and log. Well, half of log. Next class we'll be solving logarithmic and exponential functions. Today is about exponential, exponential graphs, exponential word problems, and then at the end we'll be going over log rules. And so the reason why today is so intense is because last year district did not allow us to teach log rules. They said that we couldn't teach anything further than what we had taught in school. We managed to let them, we managed to get them to let us teach logs and exponentials, but they said you can't go any further than introducing logs and exponentials, so we never got to log rules. So the second half of notes today may seem really, really foreign. Just breathe and know that you can always ask questions or watch the video later. Okay, so let's go ahead and start. We're starting with exponentials. Now here we have two exponential graphs. Exponential graphs are either growth functions or decay functions. Which one do you think displays exponential growth? The left one or the right one? Yes, for sure the left, right? We always read a graph left to right. So this graph is increasing from left to right. Therefore, this is an exponential growth function. Exponential growth. Whereas the right one, reading left to right, we are decreasing. Therefore, this one is an exponential decay. We're decaying. We're dying. We're decreasing. And exponential functions are always written in the form y equals a times b to the power of x, where both a and b are real numbers, and they're not zero, so they're non-zero. Can't be zero. A is referred to as the initial value, so your starting value, or it's also in a word problem, your y-intercept. So this would be like at times 0, what your initial value is, what your starting value is. And b, because it is the number that has the exponent on it, b is referred to as your base. It's your base number, or as the growth decay factor. I just realized that I was not this. Now, clearly we can see here, or I hope that we can see, the reason why these are exponential equations or exponential functions is because you have a variable in the exponent. That's what makes these exponential. Okay? So let's talk about what is an exponential function and what is not an exponential function. Is f of x an exponential function? Yeah, right? It has x, it has the variable as the exponent. What about b? No, right? The variable is the base. It is not an exponent, so this is not an exponential function. What about c? Yep, variable is an exponent. What about d? Yeah, even though it's a negative, it's fine. It's still exponential because the variable is in the exponent. And what about e? Nope. Even though it looks like it, pi is not a variable. It's a number. It's a constant. And then we're going to skip part 2 because it's just too easy. All you're having to do is plug in values and find their value. All right. So sorry if I'm going too fast. Part 3 is now taking data sets and creating the exponential function. Now we're going to skip f and h and we're just going to do g. So we're looking at both our x values and our g of x values, or y values. We know that exponential functions start off as our a value times our base raised to the power of x, where a is the initial value. So what is your initial value for g of x? At time 0, when x is 0, yes, exactly. It's 8. It's not just 32, because that is not the y-intercept. That is not the initial value on your graph for time 0. Instead, it's not erasing. Instead, at time 0, or at the x value of 0, our y value is 8. So that's how we start our exponential function. And then comes our growth factor or decay factor. Now, in this case, is this a growth or decay? Clearly a decay. We're going down. We're going down. We're decreasing each time. Does anyone know how to find the decay factor? Dio goes, no. Ruby said it in here. We have our first y value is 32. And we ask ourselves, what do we do to 32 to get 8? Now, I'm not looking for a plus or minus here. What I'm looking for is a multiplication. Now, I know you think in your head, okay, you divide by 4, but it has to be what you multiply by. Yes, what you multiply by. So you guys are correct. We're multiplying by a fourth. And that is our decay factor, but we have to check, okay, is that consistent? If it's not consistent, then this is not an exponential function. So to get from 8 to 2, do we multiply by a fourth? Yes, we do. To get to 2 to 1/2, do we multiply a fourth? Yes. 1/2 to 1/8. Yes, you multiply by a fourth. And 1/8 to 1/32. Yes, you multiply by a fourth. So this is truly our decay factor. So this was our initial value. This was our decay factor. And this function is not complete. Oh no. It's this, I need to get a better, I have a better headset at home. It's just I want to leave that at home. I guess maybe I'm going to have to buy another better one for here. It's fine. It's fine. But anyway, what would complete this exponential function? Is this exponential right now? No. It's a constant, right? 8 times a fourth. Okay, great. Yeah, we need a variable somewhere in here. And we know this is an exponential function because we're multiplying our y values each time. That's how I know it's exponential. Multiply y values. So I know this is exponential. There needs to be a variable on my decay factor. Any questions? You did this, I know it was years ago, and you're probably so sick of me saying this, but you did this a bunch in Algebra 1. You did this a little bit in Algebra 2 just because your year was cut short. Okay, so now let's just talk about these first two exponential equations. Oh, sorry. Are you going to do f of no, I'm not. I'm not. I mean, the same rules apply. You write down the initial value. So this one's 4, this one's 3/2, and you find what you're multiplying by each time. So this one you're multiplying by 3, by 3, by 3. So this would just be this function. And then you're figuring out what you're multiplying by each time. This one is by a half, by a half, by a half. So this would be this function. We're on a tight schedule. Yeah, we are. All right, so here we go. On this first equation, what is this, a growth or decay equation? It is decay. How do we know it's decay? Our factor is less than 1. Our factor is bigger than 0. It has to be bigger than 0, but it is less than 1, making this a decay. Therefore, what about this function? This is bigger than 1. It is a growth. What is our initial value for, we'll call this A and call this B. What is our initial value for A? 3, right? It's that number out in front, that A value. What about our initial value for B? Yes, 3/4. Now, we're trying to find, in part A, our growth factor. What are we multiplying by each time? 0.45. Therefore, our growth factor is what in part B? Well, Jessica's answering in the chat quite. Oh, there we go. Someone else. Dario. Now, here comes maybe the tricky part. Maybe. Let me help Jessica. We now want to know what our percentage of decay is. It's not, though. It's not 45%. How much are we decaying? It is 55%. Yes. Yes, it is 55, right? If we multiply, say, 1 by 0.45, that gives us 0.45. We've actually decreased by 55%. And the way that we get this mathematically is we take 1 and we subtract, when we're decaying, 1 minus our decay factor, which is 0.45. And then, of course, because we want a percentage, we're going to multiply that by 100. So 1 minus 0.45 is 0.55 times 100 gives us 55% as our percent decay. Then, who knows how we could find our percent growth? So if I did 1 plus 2.45, that would be you saying we are increasing by 345%. Anybody? Yes, Dario! Well, oh, kind of. It is 145%. Dario is so close, so super close. If we did it the way Dario is saying, it would be a negative number. Oh no, is my mic bad? Oh, Jesus. It's fine. Right, exactly. You do your growth factor minus 1. We're taking out the 100%, right? We're taking out the full initial value. We don't care about it. We just want the percent of growth. We want to know how much more than the 100% we have. So we're doing 2.45 minus 1, which gives us 1.45 times 100 gives us 145%. Does that make sense? At least the mic isn't muted. True. Sure. You know what? No, never mind. All right. So now just really quickly, just because we want to show you and we want to talk a little bit about E. I did talk a little bit about it last class. I did talk a little bit about last class, but what is E? What does E represent? Yes, Euler's number. And the reason why Euler's number is so special is because it appears in nature quite a bit, or in the real world, you can think of it as. So when we're compounding continuously, you use Euler's number. When we are trying to figure out populations, sometimes we use Euler's number. It appears a lot in the real world. That's why it has a very special log that is the inverse of Euler's number. Do you know what that is? ln, yes, ln. ln standing for natural log. But of course, they wanted it to look more like a log, so they just flipped the letters. So instead of it being NL, it's now ln. Yeah, they wanted it to appear more like a log because it already doesn't look like a log, so they just flipped the letters around. Now, if we're looking at this graph over to the right here, this bottom line is what we think of as our parent function for exponential. Parent exponential function. Whereas the steeper exponential function is the Euler's number graph. So I hope that this makes sense to you. Our base is just a little bit bigger. Our base is just a little bit bigger, meaning that my rate is just a little bit more, meaning that my graph should be steeper, right? And what E is on this graph is the value as 1 plus 1 over n to the power of n approaches as n becomes infinitely large. So as n gets bigger and bigger and bigger and bigger, this entire expression approaches 2.7182881 blah, 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 blah. That's what Euler's number is. And this should look familiar to you, this 1 plus 1 over n to the power of n. It should look familiar to you. That's, which one is it? Which finance equation? No. I think it's the n numbers, n times a year that interest is compounded if your time was 1. It's not continuous interest. Continuous interest is this, PERT. Which makes sense, right? All of a sudden, when we're compounding continuously, that means n is infinitely large, right? N is infinitely large, creating Euler's number. It's kind of a mind blower, but it's really interesting to think about, right? As you're compounding more and more and more and more often, you're getting closer and closer to Euler's number, replacing E in your equation. Isn't that crazy? To me, it is. Okay, sorry, I'm getting off track. Let's keep going. All of this graphing, we have done a million times, and we've talked all about how to find all of these things a million times, right? Domain, range, y-intercept, transformations. Is it continuous, discontinuous? Is it increasing, decreasing? Is it symmetric? Does it have a bound? What are its extrema, asymptotes, and end behavior? So to save us time, because I really want to spend more time on log rules, I'm not going to fill this out, and instead I'm going to put it on the key online. Okay. Also, we're not at all this year ever having to, or I'm not testing you over graphing by hand, right? Because we're virtual and I can't grade your blank graphs. So this is kind of, I don't want to say pointless, but I don't need to go over it right now. I hope everyone's okay with that. Oh my gosh, there's so much to get through. Okay, so now we're going to move on to exponential word problems. This first part is fairly easy. So it gives us the standard growth and decay formula, and then it gives us some values. It gives us the initial value for A is 52, and it's increasing at a rate of 2.3% per day. And it wants us to create what is this time the growth function. So how do I start this off? Yeah, you take your initial value. I'm on the wrong page. That's why I was like, what the heck? There we go. 52. And then what? 1 plus our rates. Now, I'm not going to put 2.3 in for the R. 2.3 is the percentage. I need to know my rate. How do I take a percent and find the decimal? Yes. So I need to take my decimal place and move it 2 to the left. So this becomes 0.023. That's what I input into my equation. And it's raised to the power of t. So this whole thing becomes 52 times 1.023 raised to the power of t. Yes, Jessica, you had it. The next one is decreasing. Therefore, this is a decay formula. So we have f of t is equal to the initial value, which is 5, the initial population. And then we have 1 minus our rate. So we need to convert this into a rate by moving the decimal place 2 to the left. So this becomes f of t is equal to 5 times 0.9941 raised to the power of t. Now you may be thinking in your head, but Ms. Sunderland, you just told us that growth, you take your rate minus 1, right? You may be thinking that in your head. However, what we're actually doing this time is going backwards. Before we were trying to find our percent. So if I scroll up, we were trying to find our percent of growth or decay. This time we're given our percent and we're trying to find the factor. So we're having to go backwards from what we did before. So you can see here that if they had given us 145%, it would have been, right, so it would have been 1.45 plus 1 gives us 2.45. So we're just going backwards from what we did before. Okay. Any questions on these first two exponential modeling, creating the exponential equations? 5 people, what a terrible word problem. Okay. So now these problems are actually pretty easy. You're going to like them, or at least I like them. Half-life formulas. Half-life formulas are great because they always have the same base of 0.5, right? It's a half. And A is our initial value, and then we divide our time by the half-life, how long it takes for half of the substance to disappear or die, however you want to think about it. So in this first problem, it says express the amount of substance remaining as a function of time t. And it says the half-life of a certain radioactive substance is 65 days. So this is our half-life. This is our h. That's how long it takes for half of it to die. And 3.5 is our initial, that's our a. So our function becomes f of t is equal to our initial value, 3.5, times the half-life, half is 0.5, raised to the power of t divided by how long it takes for half of it to die. Done. I'm sure that you did this in chemistry, I think. Pretty sure. I don't know how I'm always curious, like, how math teachers compare to chemistry teachers. Like, do we teach it in the same way? I don't know. I have no idea. Okay. Oh my gosh. Don't even. Did I ever tell you guys that's the one class I dropped in college? Was Chem 2. I just, like, chemistry in high school, easy peasy. Chemistry 1 in college, so it's chemistry 101 in college, was like easy. Chemistry 102, or was it 201? I think it was 201, I just couldn't do it. I'm not really good at memorizing, and it was all about memorizing. Oh my God, I'm getting so off topic. Sorry. Okay. How much of the substance will remain after 25 days? And how did you get that, Ruby? Oh my gosh. Yes, exactly. So all we have to do is take this 25 days and plug it in for t, and then, so I can show you my calculator if you want. No. Okay. So we have, now what I'm going to do actually, I'm going to be special about it. Oh my God, come on. Maybe I won't. New batteries. Wow, what is happening? Okay, maybe I won't be special. Oh, there we go. I'm going to put this into y equals. The reason I'm going to put this into y equals is because it's going to be it's going to make doing part C easier for me. So here I have 3.5 times 0.5 raised to the power of x. Oh my. Yes, this is why Desmos is better sometimes. X divided by 65. Now, whenever I'm trying to find specific y values based on x values, I can look at my table. And I'm trying to find the time 25. So I'm going to scroll all the way down. Wow. Wow. It's okay. Don't make fun of me. Listen, I need to hold on to my old technology. Yeah, Texas Instruments they need to progress and they don't. Okay, 2.681 grams. But then now, part C says approximately when will there be less than 1 gram remaining? Yes. So here, the reason why I took all this time to plug this in is because I now have a specific Y value, right? This is a gram. This is the amount of the substance that is left, and we're trying to figure out when this happens. So what you do is you plug this into Y2, and you graph it. And of course, our window isn't big enough. We need to go more to the right. So I'm going to increase my X max to be, it doesn't always work. So that's why, so what Ruby was saying is there are ways that you can hit zoom and adjust your window, but it doesn't always work. So sometimes it ends up creating more work for us in the end. So I personally like to adjust my window myself. Okay, and then all you have to do to figure out where they intersect is hit second calc, 5, enter, enter, enter. And we get 117.478, and this is a time. Our time is measured in days for this problem. Approximately when will there be less than, yeah. All right, any questions on that number 2 problem? It did take forever, yeah. Oh, you on the graph kept scrolling? Oh my gosh. All right, so here, I don't even think I'm going to do number 3. It's too easy, actually. It may look, so this is what they love to do to you in math, is create a problem that looks crazy and then just expect you to plug in. That's all that this problem wants. It gives you a height and wants you to find the pressure. So all you have to do is where you see H, you're going to be plugging in 8.2. So this is 14.7 times 0.5 raised to 8.2 over 3.6. And you just plug that in the calculator and you actually get 3.031 lbs in inches squared. And then the second one is also easy because it just wants you to find the height, so the H value given the pressure. So this time the pressure is 2.5 and it wants you to solve for the height. Now we haven't gone over this yet, how to solve for this. So instead what you can do is just plug both of those, plug this equation into y equals and plug this equation into y equals and figure out where they intersect. And you would end up with H is equal to 9.2 miles. Okay. I am working on getting number 4 thrown out. The reason I'm working on getting number 4 thrown out of the test is because not all of you, and actually in the chat right now, just real quick. So once you fill out your list, you go to stat calc, and then you go up to exponential regression. Now, while you're here, if you don't store this into your y equals, instead you type it in, you will get this problem wrong. You'll get the part C and part D wrong because if you're typing it in, you're actually having to round these values. And rounding values creates wrong answers. What you need to do is you need to store this regression equation by hitting alpha trace, I think it is. Yes, it'll pull up y1, you hit enter. And then you can calculate, and then it will put the equation in y equals for you. It automatically puts it, it won't round anything. This is the only way to get the correct answers here. So if you don't have a graphing calculator, Desmos doesn't do it accurately, nothing we found does this accurately, so we're kind of stuck. My husband's calling. So I'm working to get this one thrown out. You might have to do it on your homework. If it marks you wrong, let me know, and I'll give you the credit back, okay? All right. Now for the good stuff. And I'll try to go through this as slowly as I can. We only have 15 more minutes. This is the part that I was rushing to get to because you've never been exposed to this before. once you get the hang of it, it is actually quite easy. It's just applying rules, logarithmic rules, to problems. And you'll never have to memorize these rules. I think it even gives them to you on the SAT. Like, this isn't something you'll have to memorize. Now, what I'm going to do, just so that we can more easily reference these rules, is I'm going to label them A, B, C, D, E, F, G, H, I, J. And we're doing three things. We are evaluating logs, we are expanding logs, and we're also going to be condensing logs. Then, just kind of as an afterthought, we're going to be using the change of base formula. Okay. You know what?